I wish I learned this trick about integration by parts a lot sooner because it saved me so much time. Let's face it, one of the most difficult parts of integration by parts is picking the right u and dv. This choice decides what we get for du and v, which determines how we set up the latter half of the equation. We want the integral that we get to be as simple as possible. As you can see, what we pick is pretty important. While both integrals are multiplied by a constant and have e to the x, one is much simpler than the other. The original integral started with an x squared, and the top has an x, compared to the bottom, which has an x to the power of 3. Now, you may be thinking that this integral is still not looking too great. To solve it, we'll have to run integration by parts one more time, but it's much closer to the solution than the other option. All that to say, how do we pick what to use for integration by parts? An acronym that we can use as a blueprint is LIATE. L-I-A-T-E. This trick helps us decide what to pick for u. The first letter, L, stands for logarithms. The I stands for inverse functions. The A stands for algebraic functions. T stands for trigonometric functions. And the E is for exponential functions. When you encounter an integral that requires integration by parts, the function that appears first on this list should be set to u. Whatever function you have left should be paired with a dx to make dv. Now remember, we use integration by parts when we come across the product of two functions, like this definite integral whose bounds are in terms of x. So what should we set u to in this case? Well, taking a look at the LIATE acronym and reminding ourselves what the letters actually stand for, we see that there are no logarithms in this integral. There also aren't any inverse functions, but x squared is an algebraic function. That's what we should set u to. That's because in LIATE, algebraic functions rank higher than trigonometric functions. So the sine of x gets to be with dx to make dv. Alright, now we just follow the integration by parts procedure. We need du and v, and to find du, we can take the derivative of u with respect to x. According to the power rule, that's 2x. So du is 2x dx. And since we know dv, we know that the derivative of v with respect to x is sine of x. Knowing our trig derivatives, we know that the derivative of cosine of x is negative sine of x. We want the positive sine of x, so we can just multiply both sides by -1, and we find that the derivative of the negative cosine of x is sine of x. Awesome. Now we have everything we need for the second part of the equation. We know that u is x squared, v is negative cosine of x, and since this is a definite integral, we must remember to evaluate this product at our bounds, x equals 0 and x equals pi. The following integral will also be a definite integral with the same bounds, where v is negative cosine of x and du is 2x dx. Now, for the sake of simplification, I'm going to move the negative signs out to the front, and the constant can also come out of the integral. At this point, we still have an integral that we need to evaluate. But before we do, notice that this integral is simpler than the one we started with. We went from x squared in a trig function to an x and a trig function. That's exactly what we want. Now, this integral again contains the product of two functions, which means we'll have to use integration by parts again. That's the perfect learning experience because out of these two functions, cosine of x and x, which should be used for u? Well, let's consult LIATE. There's no logarithms, no inverse functions, but yes, there is an algebraic function, x. So once again, the trigonometric function can be paired with dx to become dv. For du, we take the derivative of u with respect to x. That's the same as the derivative of x to the power of 1, which is just 1. So du is 1 times dx. Using what we have for dv, we know the derivative of v with respect to x is cosine of x. The derivative of sine of x is cosine of x, so v must be sine of x. Nice work. Now to set up the equation, we know that u is x, v is sine of x, u times v is evaluated at the bounds, and we subtract the definite integral from 0 to pi of v times du. And we can't forget, this entire thing is multiplied by 2. Alright, look at this integral. Remember earlier we found the integral of sine of x dx. That was negative cosine of x. This is a definite integral, so all we have to do is evaluate this from 0 to pi. If we put that into our formula, the two negatives make a positive. And we are evaluating both of these from 0 to pi, so we can just evaluate them together. Okay, why don't we go ahead and evaluate this integral first? We are evaluating x times sine of x plus cosine of x at pi and 0. Using our trusty unit circle, we know that at pi radians, sine of pi is 0 and cosine of pi is -1. Pi times 0 is 0. So this first part is just -1. Okay, what about when x equals 0? Right off the bat, we know that 0 times anything is 0, and for cosine of 0, we can check the unit circle again, and we see that cosine of 0 is 1. So this produces -1 minus 1, which is -2. We just evaluated this part right here. And in the midst of all that's going on, we can't forget to multiply by the constant, 2. 2 times -2 is -4. We're almost done. Going back to the equation with the original integral, we know the value of this integral is -4. And now, to fully unlock the answer, we just need to evaluate -x squared times cosine of x at pi and 0. When x equals 0, x squared is 0, so the second term is just 0. And when x equals pi, we can take a look at our unit circle to find that cosine of pi is -1. So this is just -pi squared times -1, or positive pi squared. And substituting this into our answer, we find that our fully evaluated integral is pi squared minus 4. Great work. By using the LIATE trick, we saved ourselves some guesswork and were able to decisively pick a value for u, which made integration by parts a lot easier. I hope you found this video helpful, and if you did, subscribe. These videos are a lot of fun to make, but they also take up a decent amount of time. So if you enjoy watching these, or if they've been helping you in any way, be sure to hit that thumbs up button and share this with friends. Thank you so much for watching.